Another from magnetism. Now things are going back to back. And it says a square loop is carrying a steady current I and the magnitude of its magnetic dipole moment. Yes, we know every current carrying loop behaves as a magnetic dipole. So there I'll be getting M will be equals to I multiplied by L square, where L is the side of the square. The first sentence helps me generate first equation. If the square loop is changed to a circular loop, all right, so when it changes to a circular loop, quite obviously, the related equation is L equals to 2 pi R. The perimeter has to be same, right? And it says it carries the same current. We need to calculate the magnitude of the dipole moment of the circular loop. In terms of M, quite obviously, that's very clear. So here M dash would be equals to I multiplied by pi R square. That's a new magnetic moment, and you can easily calculate it in terms of the previous magnetic moment. You do this, and question number 2 would be the correct option for 25th question. Time to proceed to the next one. 26th question is a nice gift. The question though seems a bit lengthy, but you see solution wise it's a single step one, and this sort of question is also essentially required in examination hall. Time to time a psychological booster is required. Well, a submarine experiences a pressure of so many pascal at a depth d1, and when it goes further to a depth of d2, it experiences a pressure of this much. And the density of water is there. That means during this given moment, the density does not vary. That's a straight conformation. We can do it on the basis of the language of the question. That inference can be drawn. We need to calculate the difference in the depth d2 minus d1. Therefore, I said nothing can be a better gift than this. The pressure difference at 2 points would be equals to rho g d2 minus d1. And you put all those things, option number 3 would be the correct one. All right, now let's go to the 27th question. 27th, elasticity, a straightforward one. Now here the question says the elastic limit of brass is 379 megapascal. So if the stress exceeds this, the brass wire is going to snap. Now it says what should be the minimum diameter of a brass rod if it is to support this much? You know, larger would be the diameter, less would be the chances of snapping. But for this given condition, the load is there, I need to calculate the minimum diameter. I cannot go below than that, right? So let's see, the elastic limit is there, which is 379. So let me write the elastic limit, which is the stress, and minimum diameter I need to calculate, and this is the case at the instant of breakage. The stress would be force divided by pi d square by 4, the cross-sectional area. You calculate it, just be careful with the unit. Option number 2 would be the correct one. Now it's time we move to 28th question.